In addition to the great success of the space journey, there is a name, and it is not James Webb. It has now been 47 years since the Voyager probes have traveled the vast expanses of space and continue to provide us with new insights into the unknown cosmic worlds. As humanity's farthest outposts, the probes have ventured into interstellar space, revealing that the regions at the edge of our solar system are even stranger than we thought. But how can we explain the strange phenomena the probes have recorded at the threshold of our solar system? And what about the gigantic and mysterious ring-like structures that hide within the heliosphere? Looking back, the year 1977 seems almost otherworldly. It was the year when Jimmy Carter became President of the United States, when the guillotine was used for the last time in France, and when the cult film Rocky won 3 Oscars. But as everyone knows, in 1977 something else took place that continues to resonate today. The launch of NASA's 2 Voyager spacecraft, Voyager 1 and Voyager 2. The first probe to say farewell to Earth was Voyager 2, launched on August 20, 1977, to explore areas of our outer planetary system that had been largely unexplored. Voyager 1 followed 16 days later on a different trajectory. At the time, no one could have predicted that these missions would mark the start of the longest space journey in modern history. At the beginning of the program, it was not anticipated that Voyager 1 and Voyager 2 would eventually travel distances of 24.63 and 20.59 billion kilometers, respectively, from Earth. As mentioned, the probes were initially tasked with gathering new information on the outer planets of the solar system. At the outset, the mission was not under the best of stars. Communication with Voyager 2 encountered issues from the start, but fortunately, NASA specialists quickly solved the problems and paved the way for a record-breaking mission to discover unknown worlds. Today, we live in an era where the James Webb Space Telescope offers unprecedented details of exoplanets in distant star systems. But nearly 50 years ago, the situation was very different. When Voyager 1 and 2 launched into space, our knowledge of distant planetary worlds was limited. The early research focus was on the systems of Jupiter and Saturn, and scientists soon gathered many measurements and pictures. As a result, our understanding of the gigantic gas giants and the iconic ringed planet advanced to a new level. It was also time for Voyager 1 to head toward interstellar space. The journey of Voyager 2, however, held some exciting stops along the way. A key maneuver in the spring of 1980 set Voyager 2 on course for Uranus, which it reached on January 24, 1986. By that time, Voyager 2 had already exceeded its original mission duration by twice the expected time. Yet, the spacecraft had little regard for Earth's predictions, and not only examined Uranus closely but also discovered 10 previously unknown moons orbiting the distant ice giant. The next planned stop was Neptune, and this was to be the final chapter of the research mission. However, Voyager 2 did not merely take routine photographs of the planet. It also revealed 9 previously unknown satellites and explored Triton, Neptune's largest moon. Triton, which had been known at the time, was studied in detail. Voyager 2 discovered that its diameter was not the 5,000 kilometers originally thought, but only 2,760 kilometers. It also revealed that the moon's brown and white surface had surprisingly few impact sites, and that many geysers were actively venting nitrogen gas onto the environment. As Voyager 2 journeyed into interstellar space, it was on track to reach the next stage of the program. To understand the arrival into interstellar space, we must turn the clock back to 2012. This is not surprising, as this distant region, beyond the powerful reach of the Sun, is not exactly around the corner. This far-off cosmic realm is filled with interstellar matter, primarily consisting of dust, atomic and molecular gas, as well as ionized particles. While this interstellar matter forms the interstellar medium, it is further influenced by the galactic magnetic field and electromagnetic radiation. When Voyager 1 crossed the boundary of the solar system in 2012, its twin followed suit in November 2018. As the spacecraft once did at the planetary frontier, they are now taking unprecedented measurements of the environment. Since the 2 probes are not traveling in the same regions, scientists have had the exciting opportunity to study the interstellar medium at 2 different locations and compare the data. Consequently, an important task for Voyager 2 was to verify the data gathered by its twin, looking for similarities and differences. In fact, much of the data from Voyager 1 is being confirmed in this manner, such as the density of particles in interstellar space. However, things take a fascinating and somewhat bewildering turn when we examine the elements for which the measurements from the two probes differ significantly. To understand what Voyager 1 and 2 discovered at the edge of the solar system, it's crucial to first understand how the boundaries of the solar system are structured. Fundamentally, there is a dynamic network of magnetic field lines around the Sun, which is invisible to the naked eye. These lines act as pathways along which electrically charged particles are projected into space. This is known as the solar wind. As the solar wind spreads through the solar system, it eventually reaches the interstellar medium. However, the solar wind and the interstellar medium do not mix perfectly, and as a result, the solar wind forms a bubble in the interstellar medium called the heliosphere. Thanks to Voyager's data, we know that the heliosphere extends approximately 18 billion kilometers from the Sun, reaching into space. At its outermost edge, the boundary where the interstellar medium begins, the solar wind finally starts to give way to the interstellar medium. Before Voyager 1 crossed the threshold into interstellar space, very little was known about this region. However, the discoveries that the probe sent back to Earth immediately left researchers stunned and disoriented because many of their predictions were simply wrong. For example, the interstellar magnetic field is nearly 3 times stronger than originally expected, which means the interstellar particles are exerting a pressure on the heliosphere that is about 10 times greater than theoretical models had predicted. While these findings were revolutionary, they were also incomplete, due to a faulty temperature measurement instrument that had been malfunctioning since the 1980s. Fortunately, since Voyager 2's instruments were functioning correctly, it was able to fill in the gaps. Researchers were all the more eager to see what information the probe would collect as it approached the heliopause. Today, we know that the plasma around the probe increased in density, slowing down and heating up beyond the heliopause. The interstellar medium reaches temperatures of nearly 30,000 degrees Celsius, which is much hotter than scientists had expected. However, since the plasma has an extremely diffuse consistency, the temperatures around the spacecraft are surprisingly low. Voyager 2 discovered that the plasma crosses the interstellar space at the heliopause and in the opposite direction. When Explorer 1 crossed the heliopause, it encountered compact increases in interstellar particles, but strangely its sister probe faced a kind of particle transition that stretched over more than 150 million kilometers inside the heliopause. Even more strange was the fact that Explorer 1, about 1.3 billion kilometers before the heliopause, entered a zone where the solar wind significantly slowed down. Overall, these different anomalies represent only a small portion of the mysteries that will need to be solved in the future regarding the outer regions of the solar system. For example, we still don't even know exactly what the shape of the heliosphere is, but at least we now know that the heliopause is surprisingly wrinkled. The enigmatic structure of the heliopause became clearer after researchers from Princeton University recorded a tremendous increase in solar wind pressure of nearly 50% within a few months. They used the data to reconstruct the shape of the heliosphere and the heliopause, leading to the stunning result that the heliopause has gigantic folds extending over tens of astronomical units in space. To remind you, the length of an astronomical unit refers to the average distance between the Sun and Earth, which is about 150 million kilometers. We're talking about folds that span several billion kilometers. No amount of Botox will help here, but perhaps the information that researchers have gathered about the background structures of these folds will help us understand them better. These folds are the result of high-energy particles moving upward from the heliopause and colliding with the standard solar plasma. As a result, we now know that the heliosphere is by no means a static and unchanging entity, but rather a dynamic one that inflates, deflates, and expands again in a constant cycle. Indeed, cosmic folds continue to chase the Voyager spacecraft. Since the solar plasma smooths out the fold structures, it continues to extend. Despite the advancement of the probes, Voyager 1 and 2 are spared from the folds in their path because they are simply moving too fast to be caught by them and pulled back into the heliosphere as it inflates. However, the pursuit of the folds means that the distance between the probes and the heliosphere doesn't increase as quickly as one might think. And we would be delighted if the distance between your finger and the subscribe button now shrinks much faster than you ever imagined. Don't hesitate to click the thumbs up and subscribe to never miss a new video from us. See you soon.